Welcome back. So in this session, what we're going to do is look at a few motivating examples. What we want to do is really get you interested in differential equations and where they can arise in scientific and more generally just physical phenomena. The first example that we're going to look at is that of population growth. A population tends to grow at a rate which is proportional to its size. So the model for this statement is as follows. We say that the time rate of change of the population P is equal to some constant K multiplied by the instantaneous population P. So that is, the time rate of change of the population is directly proportional to its population at any given time. So this is the differential equation that we are looking to solve. This model makes certain assumptions. Can you think of any? So some of the assumptions that this model makes include no restrictions on resources, no restrictions on space, for example. There is no war, which would lead to fewer males at home to procreate. There might be some more that you might be able to think of. What are the units of K? This is a fairly straightforward differential equation that we can integrate directly. In fact, what you will see later on is that this is what we would call a separable differential equation. It is separable because what we can do is separate the different variables on either side. So we can have one side as a function of P only, and P being our dependent variable, and the other side as a function of T only, where T is our independent variable. So let's do that. What we're going to do is divide both sides by P, which will give us 1 over P dP is equal to K. And what we're going to do is multiply both sides of the original differential equation by dt, which will give us K dt on this side. We can now directly integrate the left-hand side in terms of P and the right-hand side in terms of T. So let's go ahead and do that. Now let's set some bounds for our integration. So we can say that our population might have an initial size P naught and go to an arbitrary population P. Similarly, for time, we can go from an initial time T naught to a final time T. We can evaluate the above definite integrals as follows. So we know that the integral of 1 over P will be ln of P. So let's do that. So we have ln of P evaluated between P naught and P is equal to, and now what we can do here, we notice that K is a constant, so this really doesn't play a factor in our integration, so we can just take it out. And so we're just going to have the integral of dt from T naught to T. So we take K out of the integration, and then all we're left with is T evaluated from T naught to T. So this leads us to ln of P minus ln of P naught is equal to K multiplied by T minus T naught. Now this left-hand side here can be simplified by noting that the difference between two natural logarithms is equal to the logarithm of the ratio of the two. So we can say that ln of P over P naught is equal to K multiplied by T minus T naught. Now, it might be worth pointing out what we're really trying to solve. We're trying to solve for p. What we want to get at is a final relationship that gives us the population as a function of time. We are looking for p of t, which will be equal to something. So how do we isolate p? We can isolate it by taking the exponential of both sides. So if we take the exponential of both sides, so we're going to take the exponential of the left-hand side and the exponential of the right-hand side, we know that the exponential of a ln is just equal to what is inside of these brackets here. So all we're left with is p over p naught is equal to e to the power of k t minus t naught. So we can come up with a final form which will just give us p as a function of time is equal to the initial population multiplied by the exponential function t minus t naught. So this is our final answer. This result is termed exponential growth due to the presence of e. We obtain this behavior when the rate of change of the variable is directly proportional to itself, as was seen in the original differential equation. So what does this look like? What does population growth, described by dp by dt is equal to kp, which leads to what we call exponential growth, what does this look like? So here, using our handy MATLAB, I plotted for an initial population p naught of 100 the population growth as a function of k. So with increasing k, so here k is increasing, we see how the population increases with time in the x direction. Can you think of any shortcomings of this exponential growth model? Would it be a useful model for predicting growth of bacteria? What about the growth of a population of humans? If this is not a good model, why isn't it a good model? If the answer is, well, sometimes it might be a good model, well, why is that so? I want you to really think about this. And if you're feeling particularly keen, maybe try to alter the original differential equation to make it a bit more realistic. We will look at a more realistic population growth model later in our study of differential equations.